So welcome to my thermodynamics final review. We'll be going over pretty much everything that is going to be covered in the final. So if I remember correctly from the email Dr. Amon sent, you will not get compressibility and you won't get isentropic efficiencies not included. She also said not chapter 1, but chapter 1 is important for, like, what I'm assuming is that there won't be exercises on chapter 1, but the stuff from chapter 1 is essential for like other chapters, so we'll be going over that as well. So we're going to first go over everything. Like I said before, it's around like 45 slides, but I'm going to go very quickly. And if you have any questions, either interrupt me, I don't really care, or post in the chat. Okay, so first part that's important, and I hope that you all know because it was covered in like the quizzes and assignments. But if that's interpolation, that's very so yeah, this is very important, especially when we're given like a quality of a fluid or a property that's in between two properties within the tables. So for example, if I have I don't know, a gas that's at 475, and you want the CP value, then you're going to have to interpolate using the values of 450 and 500 Celsius. Okay. And also, I recommend memorizing this formula directly. Even though this one makes the most sense, you can just memorize this one to derive the value quickly. Intensive vs extensive. So we call back at the really beginning of the semester. Extensive property is a property that depends on the amount of mass that you have, or the matter. So mass and volume are examples of that, but intensive properties is when it doesn't depend on matter. So for example, density does not, specific volume, etc., etc. A rule of thumb is that if you can cut the object or whatever you're studying in half and the property remains the same, then the property can be deduced intensive. If that's not the case, then it's deduced extensive. So like if you're cutting an object that's red, also it'll remain red throughout. So that's also an intensive property. Pressure questions. So you definitely won't be getting pressure questions for the final, but what's important to remember is just the difference between absolute pressure and gauge pressure. So gauge pressure is the difference between absolute pressure and atmospheric pressure. Absolute pressure is your pressure relative to vacuum pressure, so zero pressure. So let's take, for example, a car tire that's has a gauge pressure of 100 kilopascal. So that's with reference with the atmospheric pressure. Now, if we were to take the absolute pressure within that tire, you would add this value, so 101.325 kilopascal. So that would make 201.325 kilopascal. Usually in exams, they will give that to you, but you're never too sure. So I would memorize this value as well. So again, if you get a car tire that has a gauge pressure of 100 kilopascal, that means that your absolute pressure within that tire is 201.325 kilopascal. So it's either in reference with your atmospheric pressure or with your vacuum pressure. And you definitely won't be getting these types of questions. Just in case, just remember that if you're in a fluid, or well, it could be air, it could be water, whatever, and you're at the same distance relative to the surface, usually it's noted by these lines, then you have the same pressure, no matter the geometry. It's just if you are in the same fluid, then you're at the same pressure. Pressure also can be denoted as the density of the fluid that you were in times the gravitational acceleration constant times the height. So for example, if you wanted, in this case example, to calculate the pressure all the way at the bottom of the fluid, well, these three fluids actually, you would need to calculate the pressure for each of these fluids. And I believe that, so density of this guy times G times its H then do the same for this guy, then do the same for this guy, and you would get your pressure at the bottom. On. General equations that are, I would say, are very important to know, not just for this course, but for many other courses, such as fluids, heat transfer, even like some technical electives that I've been taking recently. Just assume that you know these equations. So, well, density can be found using its units usually. So it's kilograms divided by meters cubed. So that's kilograms associates to mass, and meters cubed is associated to volume. And density, you remember, is the opposite or the inverse of specific volume. So the volume divided by the mass, meters cubed divided by kilograms. Then you have specific gravity of a fluid. So that'll be the density of the fluid of whatever you're studying, it could be mercury, whatever, divided by the density of water. So this is where you're going to need either, just like with atmospheric pressure, I wouldn't take my chances on the exam giving you the value of density of water, which in SI units would be 1,000 kilograms per meter cubed. Or in imperial units, 62.4 pounds divided by feet cubed. Okay, and then yeah, specific weight, that's going to be the density of the fluid that you're studying times the gravitational acceleration. Which also actually, you can replace the rho times g in here by the specific weight. So it could be the gamma letter times the height. Makes easier. And yeah, obviously, constant gravitational acceleration, you should all know this by now, 9.81, and an imperial 32.2. It's acceleration unit, so meters divided by seconds squared, or feet divided by seconds squared. Okay, moving on. I'm gonna skip this because you're not gonna need this. Quality is actually probably going to be in the exam or in some way, shape, or form, just to make sure that whoever is correcting knows what you're doing. So quality, by definition, is the mass of the saturated vapor divided by the total mass. So this pretty much, if your x is equal or above 0 and equal and below 1, that means you are in the mixture phase. That means whatever fluid you're studying has both saturated vapor and saturated liquid. And so what this tells you is how much vapor you have in your total fluid that you're studying, how much vapor relative to the total mass. So usually denoted by the subscript G for vapor and subscript F for liquid. So total mass, it'll be the mass of the saturated liquid plus the mass of the saturated vapor. And that's the first, that's mostly the definition. You probably won't be using this equation for quality. Actually, I think it's in that. Yeah, this will be, if you're trying to find quality, this will be the equation that you're going to be using, where y can be replaced by any intensive property. So it could be specific volume, could be density, could be specific enthalpy, et cetera, et cetera. So the y here without any subscript is whatever you have found. So let's say you're in a fluid, you have, I don't know, 25% of saturated liquid and 75% of saturated vapor. Then you have a specific volume associated to that. Then it's going to be minus the intensive property, but for the saturated liquid. So again, with the example of specific volume, when you're at saturated liquid, that means that your quality is equal to 0, right? So because that means that you have no saturated vapor within your total mass. So mg would be equal to 0 divided by mf, so equal to 0. So you would be here, you'd be at A if you're looking at your P or TV diagram, and you would take this specific volume of the saturated liquid, which you would find from your property tables, but we'll go over that a little bit further. And then you divide that by y subscript fg. Now subscript fg, we'll go over that again a little further, but just a quick reminder that, again, you replace this by any intensive property, but subscript FG pretty much means that it's going to be the whatever intensive property of the saturated vapor minus whatever intensive property you're using of the saturated liquid. They have to be the same intensive property, but it's just the difference between whatever property you're using for the saturated vapor minus the property at the saturated liquid. So if we would take this example of the saturated, specific volume, it'd be this specific volume minus this specific volume. So that's usually like a quality equation that you'd be using, but the most popular one is actually this one. So in a lot of the exercises that I see, you'll be given the quality already. So I don't know, like 50% or 95%. And you're trying to find the property at that quality. The next example is specific volume again. And pretty much it's just a reform of this equation. They put this character on the other side and this character on the other side, and they obtain this equation. And so again, you take the specific volume of the saturated liquid plus the quality times the difference of the specific volume of the saturated vapor minus specific volume of the saturated liquid. And again, the specific volume here could be replaced by any intensive property. It could be specific enthalpy, it could be specific, could be entropy, it could be whatever. Yeah, okay. Moving on. Oh yeah, and go over the same thing again. So if you have a property at a quality, this is the equation that you would use to calculate that property. Okay, PV or TV diagrams. There are some questions that ask you, could you draw the PV or TV diagram for whatever process that you're using? And so it's important just to not memorize like all PV or TV diagrams and what they look like. They all look relatively the same. They'll all have either P or T on the y-axis or whatever intensive property on the x-axis, most of the time specific volume, and they'll all look like a bell curve, kind of, sort of, yeah, like a bell, and have this shape. And it's also important to memorize kind of what they represent. So if you're at in this case scenario, like a very low specific volume, and you have, well, usually any value of pressure, you'll be in the compressed liquid region. So if you take water, for example, that has a very low specific volume, but any value of pressure, it'll be in a liquid form. You go a little further with heighten your specific volume, and you hit the saturated liquid line. So this is where you're on the verge of starting to create vapor in your fluid. Go a little further in the specific volume, and you're in the saturated liquid vapor region. So what we call the mixture phase. You'll have both liquid and vapor within your fluid. How much? That depends on the quality. If you have, if you're close to 0 in your quality, or 0%, then you're closer to the liquid region. If you're close to 1 or 100%, then you're getting closer to the vapor line. If you're at 1 exactly, or 100, then you're directly on the saturated vapor line. If your quality is equal to 0, then you're, saturated vapor line. If your quality is directly equal to 0, then you're on the saturated liquid line. So x is equal to 0 for here, x is equal to 1 for here. Yeah, I think, oh, and then, yeah, once you hit the vapor line for whatever specific value, and then you go a little further, then you hit the vapor region. So your whole fluid has turned into a vapor. Yep. So usual way to use these diagrams is through like multiple, well, it's I forgot what the rule was called, but pretty much the rule to distinguish almost all properties is to have 2 intensive and independent properties. So let's take here, for example, they have given an example for us at a temperature of 374.14 Celsius and a specific volume of this value right here. Within the bell curve at this specific pressure of 22.09 megapascal, you draw the line of the temperature horizontally. Right when it hits the bell curve, you go all the way down, and this is your specific volume. Okay. Now let's say, for example, that we are at a pressure of 8 megapascal and our temperature is at 250 instead. Let's see, right above here. And you hit the line somewhere. Well, you hit here. You hit this whole region. Now what happens here is that your temperature and pressure are no longer independent from one another, pretty much. So you can't use the rule of I don't remember what the name of it is, but where you can find any other property using two independent intensive properties, because temperature and pressure now become dependent with one another. So if you were, this is the mixture phase, back if you remember looking at the previous slide, and you had a temperature of 250 Celsius and a pressure of 8 megapascal, then you wouldn't be able to find the the specific volume for that property, or well, any other property for that matter, actually. You would need another property, maybe quality, for example, that's considered an intensive property that's independent from anything, or I don't know, specific enthalpy, et cetera, et cetera. They could be any other type of property, but here you can't just use temperature and pressure in this case. Now, if you're anywhere else within the graph, so if you're, I don't know, if you're a little more above, or you have a higher pressure and it hits the line at a different point, you have a different specific volume, et cetera, then temperature and pressure become independent from one another, and you can find any property. Triple point, I think that's, you're not going to be asked much of that, besides maybe the definition, which is just the state in which the substance exists in all three states, so liquid, gas, and solid. And that can be reached. I don't know if your teacher showed you, like, it was a pretty cool video of it with water, but if not, just look it up online. But I would just memorize the definition. Okay, so this is very important, especially if you didn't do very well in the first quiz. I don't think there was any of the other types of examinations that would kind of test you on property tables, but it's very important to know how to use property tables. This is definitely going to show up during the final exam. Maybe not the whole property tables pack that you see in your Moodle page, but definitely enough to test your knowledge about it. So yeah, let's actually go over it. You should all see the property tables by now. This is the one found in your Moodle page. It should be just regular name property tables. And essentially, almost all the pages are going to be helpful to you, especially when you're trying to solve exercises at home. And they definitely don't expect you to memorize all these values. So the first page covers, for a bunch of substances, their formula, but that's not really important. Their molar mass, again, that's not too important. I've rarely seen exercises using molar mass, but it can be. The gas constant, that's going to be very important, especially with the ideal gas law equations. The temperature at their critical point, and pressure critical point as well. So what is the critical point, actually? There we go. So within this bell curve, with the separated regions, so you got your solid on this side, you got your liquid here, and your vapor here. Your critical point is when the bell curve reaches its tip. So when the liquid and vapor region are together. So you can go straight, if you hit exactly at the right properties, actually, you can go straight from liquid all the way to vapor and skip this whole mixture phase if you're at the right properties, using the critical point properties. And so with these critical point properties, we're actually going to get this. Actually, no, they're no longer important because you're not going to be doing compressibility factors in your exam. So actually, you can completely ignore these. And then volume, whatever. This is not necessary. Mostly the gas constant will be important. Ideal gas specific heats for various common gases. So you get your CP and CV value for a bunch of gases. This is important when you're maybe trying to calculate specific enthalpy or specific internal energy. We'll see that in a bit. But CP and CV values for these gases can be important. Now, it's important to note that these CP and CV values are only at 300 Kelvin. So they're going to be different for varying temperatures. Yeah, sorry, I had a blank. But for some exercises, usually they'll tell you, oh yeah, you can take CP and CV values at room temperature, which is the equivalent of 300 Kelvin or roughly like 27 Celsius. You can assume you can take these values. Oh, they actually also give you K values. So we'll see that in a bit as well. But yeah, I know. So last chapter, I mean, I assume you all got the email from Dr. Iman. Maybe you're from other sections or other professor's class and you haven't received any email or confirmation about this. But usually all finals are the same for students, and you shouldn't be covering the last section of the last chapter, which is isentropic efficiencies. That won't be covered, but you're still going to be covering entropy change. So you should still memorize, know about that. So back to this, you also are given the gas constant again, but yeah, for more detail, they're given here. Yeah. Moving on, you get your CP and CV values for different gases, air, carbon dioxide, etc., but at different temperatures this time, and K values as well. This table isn't very much used. And then you have this, which could be used. This is basically a function of CP, so your constant heat you can calculate for different temperatures. So for example, we take nitrogen, we implement these constants, so A, B, C, D, within this function. We implement the temperature, and then we get the CP value for that specific temperature. Now, just be careful. This CP value is not it's not the same as this CP value. This is kilojoules divided by kilograms times Kelvin. This is kilojoules divided by kilomoles times Kelvin. So you'll have to divide this CP value by, I think, the molar mass. Yeah, you'll have to divide it by the molar mass of whatever gas you are studying. And then you'll get the same CP value from here that you can actually implement into your equations. This value probably won't be equal. Most properties are not divided by kilomoles, but by kilograms. So just make sure you remember that. Yeah, and also know how to integrate this equation, because this is probably the only integration that can be asked of you. So for example, if you're in between two processes that have different temperatures, so T2 to T1, or well, other way around, T1 to T2, then you would integrate this equation from T2 to T1. And yeah, just know how to integrate. It's a very easy integration. So I would, again, I doubt that this will be covered in a final. It can be though. This is just some random properties. They're not really useful. Same here, but for metals, for food, actually, if you're interested, for ice cream, watermelon. Okay, so this is where things get important, this is where you might need to use interpolation. So first we got the water tables. Further down we'll have for a different fluid, but first we start with water, and we start with water in its mixture phase tables. So if you remember, go back to this bell curve, we're within this region, we're under the bell curve, in between the saturated liquid line and the saturated vapor line. And this will give you all properties. Now, remember from the rule, temperature and pressure are dependent on one another. So if an exercise gives you temperature and pressure, then you can't use these properties to find other properties. You're going to need either quality or well, anything else. Any of these actually can be used. If you're outside the bell curve, or if you're directly on the lines, then temperature and pressure become independent for one another, and you can use any of the other properties, or find them, not use, find them. But if you're inside, you can't. So yeah, let's take, for example, temperature at 10 Celsius. We know that our fluid is a saturated liquid. So we can say that it's at this pressure, and we can say that it has this specific volume over here. It's at this specific internal energy value right here, this specific enthalpy value right here, sorry, this entropy value right here, etc., etc. So the idea is just that you're given maybe temperature, or maybe you're given pressure and a state, and you just need to, well, usually if you're given temperature, you would use these tables. So you would go down to, if you can see it, if you're given 30 Celsius, you go down here and then go to the right and find the properties that you need. If you're given pressure instead, go a little bit further down, so past the temperatures where they go in increments of 5s, all the way to this is the critical point actually, where it hits its limit for water. You would go down, and here instead it's with reference to pressure going into increments. Well, increments change, but I guess uniform increments. If you're given 100 kilopascal, you would go down to 0.1 megapascal and get your properties to the right once again. So these are your mixture tables. You know, if you're directly in the mixture phase, then you're given temperature and you're given pressure. Then you can't use that just to find any of the values. You'll need to get either quality or another specific property. Unless you're directly into saturated liquid or a saturated vapor, then you can use either of the properties. Yeah, so these are the mixture tables. They have either temperature or pressure as a reference all the way to the left. And yeah, so pressure goes all the way to 22.09. That's its critical point property for water. After the mixture phase tables, you go into your superheated water tables, which pretty much just means vapor, or when water is in a vapor form or a steam form. And in this case, we already know that pressure and temperature are independent from one another, so you can directly get the properties that you want if you just know these two properties. So if you have, for example, a vapor or a steam at 1.2 megapascal, and it's at a temperature of 400 Celsius, and you would like to know the specific volume, this is your pressure table that you're going to use. And this is the temperature row that you're going to use. And here, right here, is your specific volume that you can assign to that fluid. Okay, and it's the same concept with all the other tables. It's just you're given, maybe you're given instead pressure and specific volume. So 2.5 megapascals of pressure and a specific volume of let's say 17,832. You go to the pressure table, you find your specific volume that has the exact same value, and here you have your temperature and all the other properties that you may need. Okay. So again, this is still vapor for different pressures and different temperatures. Again, keeps on going. And then you go to your compressed liquid water, which is just pretty much the same thing as steam and vapor, but for compressed liquid. So in the solid and liquid state. Again, at different pressures and temperatures. Okay, and it's the exact same concept. Okay, moving on to page 17. So compressibility factor, again, not going to be covered in your final, so we can skip this, skip this, skip this, not needed. And then you're going to go pretty much, these are the exact same tables as the ones we saw previously, but for the saturated, for the refrigerant 134A. So if your exercise uses refrigerant 134A, you can expect that you're going to be using these tables. Usually it's most of the time just water, but sometimes I like to switch it up to 134A because it has different properties at different temperature and different pressure. And it's the exact same concept. So you'll have your mixture phase tables. Keeps on going with either temperature as a reference or pressure as a reference. Or you will have your vapor or steam tables, different pressures. And you don't even have your compressed liquid tables for, so that those won't be used. Those won't be needed if they're not here. And yeah, exact same concepts. Exact same rule applies as well. You need two independent intensive properties to find all the other properties. So if you're in the mixture phase and you know that you're not in the saturated liquid or saturated vapor phase, you're in between, then you can't use temperature and pressure to find the other properties. Okay, exercise also might give you not exactly two intensive properties, but they might give you maybe one intensive property and two extensive properties. But using these two extensive properties, you can get an intensive properties. The most common example is mass and volume, with which you can get either specific volume or density. So yeah, and once you have these two intensive properties, then you can find anything else. Okay. Oh yeah, so the subscript, just like I said before, is just for whatever property you're studying is going to be the difference between that property for the saturated vapor minus that property for the saturated liquid. Okay. Okay, so maybe not very useful for the final, but definitely useful for the exercises because it might get confusing. So if you're in the compressed liquid phase for water and your pressure is below 5 megapascal, then you're going to use the data from the saturated liquid data at the same temperature. So actually, let's go back to the property tables. Go to water at the compressed liquid. Right here, you see that its minimum pressure is 5 megapascal. So let's say that we have a temperature of 100 Celsius and at a pressure of 2 megapascals, but we know that the exercise tells us that it's only a compressed liquid. Then we see that in the compressed liquid water tables, it doesn't go past, lower than 5 megapascals. So what you're going to have to do is go to your mixture tables for water, all the way up at a temperature of 100 Celsius, and use, so here at 100 Celsius, and use these properties, even if the pressure is not the same. So that was quite a large margin between the two, the pressure that I gave and this pressure here. Usually they'll be a bit closer, but you're allowed to use these properties in this specific case scenario. So again, if you forget this this rule, it'll be in the slides that I'll post. Ideal gas equations. You need to know these. I don't know if they're going to be in your equation sheet, but it's just, you should practice enough just to have them in your head. just completely memorized. Maybe just one version or the different versions. If you know, you can either learn all 4 of the equations, all 4 variations, or just one and know how to go from one to the other. So for example, specific volume, remember that it's the inverse of density. So just divide, just reverse the specific volume, and you can put density over here and have this equation. Yeah, all of you should by now should know these equations. If not, just check out this slide. It covers everything. If you have an ideal an ideal gas, you can also use this equation. So in between 2 states. Yeah. So if you have a process that goes from one state to the next, so state 1 to state 2, then you can equate these properties together. If you have maybe even T1 and T2 are equal to one another, then you can just cancel them out, and you have P1 times V1 is equal to P2 times V2, and yeah, the same the same applies to the other properties. But this is, remember, for only ideal gases. Okay, specific heat. So we talked about in the property tables, the definition of specific heat, which you don't really need to know. I doubt that you'll be asked that, but just for theory's sake, it's pretty much the energy required to raise the temperature of whatever fluid or mass substance you're studying by 1 degree for either like a constant volume, which is represented by CV, or a constant pressure represented by CP. CP and CV can be calculated with these equations. So since CV usually is given to you as a constant, you can put CV on the other side of the integral. If it's not, then you're going to have to use that equation that we saw in the property tables as shown right here. Sorry. And that's for the change in specific internal energy. For you use CV integrated at the change of temperature, or specific enthalpy will be equal to, this time, CP integrated with the change in temperature. Yeah. So yeah, again, if it's not given to you, CP and CV can be given to you in the property tables at different temperatures, or maybe if it's not clear, then just assume that it's at room temperature of 300 Kelvin on page 2 of your property tables. Enthalpy. This equation is not used often during exercises. It's just for definition's sake. It's the sum of internal energy plus the product of pressure and volume. But the theoretical definition is a quantity equivalent to the total heat within a system. And yeah, I guess, yeah, that's just for theory. So in this equation, by the way, it's in intensive properties form. Usually, by the way, you can see that all your properties are actually in intensive form. You can see within the units that they're divided by kilograms, which makes them independent from whatever mass is within your substance. And usually they're denoted by the lowercase letter right here. So if you take specific volume, for example, then it's lowercase v. If you were to take volume, then it's going to be, as you all are familiar with, the uppercase v. It's going to be the same for internal energy. Lowercase u is going to be the specific internal energy, and higher case u is going to be the total internal energy. And the same thing applies for the rest. Okay, moving on. First law of thermodynamics. Now, that's definitely an equation that you're going to be tested on. General theory is just the change in energy is equal to the heat transfer, Q, minus the work. The energy can be represented in many forms, but we're only going to study 3. So there's internal energy, that's the energy created by the interaction of atoms and molecules. Kinetic energy is just how fast you're going. And potential energy is how high you are relative to whatever gravitational field you are. So in this case, Earth. And these are the equations for kinetic energy and potential energy, which can be asked of you. energy usually is represented, I think, is it covered in, oh no, it's right here. Energy unit is joule, and joule can be decomposed into newtons times meters. So actually, if you were to take work as an example, the equation for work most of the time is a force, usually in the vector form, times the distance that you're covering. So force is in newtons, and then distance is going to be in meters. So hence you get newtons times meters. And that's a joule, a single joule. So if you're at kilonewtons times meters, that's going to be kilojoules, so on and so forth. Okay, then we have the elongated version of the first law of thermodynamics. And they also modified it this time so that it's, well, they divided everything by time. So you have your change of energy with respect to time. You have your change of heat transfer with respect to time, same thing for work. And then you have your parentheses incorporating your different types of changes of energy. So you have the specific internal energy change, you have your kinetic energy change, you have your potential energy change. And usually, so you see the subscript I and the subscript E. I represents the inlet and E represents the exit. So if you're studying, for example, like a control volume that has an inlet or an exit, then these would be the respective values you would use to calculate whatever you would want to calculate. Maybe change of energy, change of heat transfer, change of work, whatever. And if you have multiple inlets or multiple exits, then you can use you would have to sum them together. One important thing to note. Oh, right. So as you can see in this equation, it's specific internal energy. In this equation, it's specific enthalpy. You can use either, whether it's more convenient within the exercise. Usually it'll be made clear, but either works. They will both, if you calculate the difference between the specific enthalpy at the inlet minus the specific enthalpy at the exit, you will get the change in internal energy, no matter what. Okay. Back. So in practically all your exercises, actually no, 100% of your exercises, dE divided by dt, so the change of energy with respect to the change of time, will be equal to 0. In thermodynamics, when we don't care about rates, that's going to be heat transfer. We don't care about rates. We only care about values and quantities. So dE divided by dt will practically 99.99% of the time will be equal to 0. Sometimes Q or sometimes work can be equal to 0, but sometimes not. Maybe it's going to be asked of you. Sometimes velocity is going to be incorporated to your exercise. Sometimes it won't be. Potential energy, again, 99.99% of the time, it will be equal to 0. So these two values, you can cancel them out. And now for the values that are always there, like all the time, it's going to be, well, either a specific internal energy or a specific enthalpy. Those values are always there. This is just the same equation, but reformatted with, well, actually, dE divided by dt is equal to 0 here, so you can reformat the equation this way. Okay, so this was like midway through the semester. Different ways that you can obtain work besides the first law equation, which we're actually, it's going to be covered here. You're going to have different processes that have specific properties to them. So, for example, there are 4 different ways that you can obtain work. For the first one, it's going to be what we call an isobaric process. So where the pressure for the whole process, from if you're changing some properties of a fluid from state 1 to state 2, and from state 1 to state 2, the pressure remains the same, then you can use this formula to find the work. The work is equal to pressure times the difference from state 1 to state 2 of volume. So that's for isobaric processes. Second way is for, I believe this is isentropic. Wait, oh, this should be, isobaric should be here. Yeah, wait. Oh, this is polytropic, my bad. This is for constant temperature. So if from state 1 to state 2, you have constant temperature, then you would use this formula. This formula can be reformatted with the ideal gas equations. If you're studying an ideal gas, then you can use the ideal gas equation to change this equation as it best suits you. Yep. Polytropic process. The definition of polytropic just means that going from state 1 to state 2 for a specific fluid can also be reversed from state 2 back to state 1. And so I'll have, I guess, multiple equations within the polytropic process that you can use. So the main one will be work, obviously. Work is equal to the pressure in state 2 times the volume in state 2 minus the same thing, but for state 1, and then divided by 1 minus n. We'll talk about that in a little bit. As well, since they're reversible, you can equate the pressure and volume in state 1 to the pressure and volume in state 2. So with this equation, where P1 times V1 to the power of n is equal to P2 to V2 to the power of n. Now, if you're studying an ideal gas, then your work equation can be reformatted this way. Actually make it easier. Makes it easier for you because you only need this time you just need the pressure. You don't need both the pressure, the temperature. You don't need both the pressure and the volume. And you also have more polytropic process equations. So this one is just a reformatted version of this one. And if you have an ideal gas, you can use these equations as well, relating the temperature change with the pressure change, and temperature change with volume change, or pressure change with volume change. If you have n is equal to 1, which never happens, is you just go back to this, which I believe it's just this. I think so, yeah. But this almost never happens. Yeah. So you can either memorize all of these. Yeah, I would memorize all these. The one thing that I'll note is that when I saw past finals, is that I did see the polytropic equations. These are quite hard to memorize, and they're often given to you in equations. But if you want to be sure, you can just memorize them yourself. Oh yeah, and the fourth way is just, well, using the first law equation. So if you're given work, for example, d divided by dt is equal to 0. Maybe your process doesn't have any heat transfer. It doesn't have any kinetic energy. It doesn't have potential energy, and the specific internal energy, etc., etc. Then you can find work if you know all the other values, or that the other values are equal to 0. Okay. Yeah. So just some tips if you prefer memorizing the equations by heart, or if you rather understand how to get the equations with the definitions of work. I mean, at this point, the final is like 4 days away, so I wouldn't take this tip very seriously. I would either memorize the equations or just hope that they're in the equation sheet. Important definition, because sometimes you'll see that in your exercise pack, something says that, oh, this steam turbine is adiabatic. This process is adiabatic. So an adiabatic process just means that your heat transfer is equal to 0. So if you go back to your first law of thermodynamics equation, this Q, no matter what shape or form it may have, will be equal to 0. And yeah, so sometimes you may be asked to calculate force, especially in a piston cylinder device. Actually, draw that. So this is your cylinder. this. I've seen some exercises, actually, I think we'll be covering one, where like you have some type of fluid in here or gas at like maybe a high pressure or high temperature that applies force onto the piston so that there's like a distance between the piston's face and the bottom of the cylinder. So therefore you can say that the gas at whatever properties it's having is applying a force to the surface of the bottom of the piston. So, and this force can be equated to this pressure times the area. So maybe the pressure of whatever your fluid is at, maybe 22 megapascal, and times the area, the surface area of the bottom of the cylinder, which usually is just a circle. So just remember that area of a circle is pi r, pi radius squared. Okay. Mass transfer balance. This can be quite important. Usually when you find exercises that say you are in this steady, your process is steady. So for mass flow rate, it's just the movement of mass within a controlled volume with respect to time, usually denoted by these units of kilograms divided by seconds or pounds divided by seconds. And these can be calculated, in multiple ways. So mass flow rate times density times volumetric flow rate. The volumetric flow rate divided by specific volume, density times area times velocity, or area density times area times velocity, or area times velocity divided by specific volume. You may either want to memorize all these equations, or simply memorize what each property's units are, and do some units gymnastics to find mass flow rate, to find the kilograms divided by seconds. It's whatever tactic you would want to use, it's up to you. I like to use the units gymnastics because it's not just useful for just this, but it can be useful for many other equations in this course and many other courses as well. Then, just volume flow rate. You saw it's denoted by uppercase V with a dot at the top. You can barely see it, but it's right there. It's just the same thing as mass flow rate, but for volume. So it's the volume of a fluid going into control volume with respect to time. Meters cubed denoted by meters cubed divided by seconds. Okay. Moving on. So yeah, to go back to what I said. So when an exercise tells you steady flow rate, meaning that the mass flow going into the control volume that you're studying is equal to the mass flow rate going out of the control volume that you're studying. So in this case example, you have m.1 and one inlet is 2 kilograms per second. The other inlet is at 3 kilograms per second. If your whole system is at a steady flow rate, then the outlet should just be these two combined together. So that's why you have the sum actually for the inlets is equal to the sum of the outlets. You can also have steady incompressible rate, just meaning that the volumetric flow rate throughout your control volume is the same for inlets and outlets. And so actually incompressible. So it doesn't directly say steady mass flow rate. It'll say steady incompressible flow rate, so that the fluid can't be compressed for a change of volume within within a section of the control volume. Nozzles and diffusers. All that you need to remember whenever you see an exercise that starts with argon gas is going through a nozzle or water is going into a diffuser is this. So usually your adiabatic heat transfer is equal to 0. Usually, work is all the time equal to 0. Remember, the definition of work is just force times distance, but no force is being applied and no distance is being covered, so work is equal to 0. Your potential energy is always equal to 0 because, well, there's no height change, so it doesn't matter. Now for kinetic energy, it's never equal to 0. That's going to be your point of interest. Usually nozzles and diffusers are going to use the first law equation, the long version of that, equate dE divided by dt, NQ, and work, and potential energy equal to 0, but kinetic energy and maybe even specific internal energy change will always be considered. So in nozzles, your velocity is increased and your pressure is reduced. In diffusers, it's the other way around. Your velocity is reduced and your pressure is increased. Just a fun fact for this applies only for subsonic fluids. For supersonic fluids, all properties are reversed. So if you had a nozzle like this, then your initial velocity would be bigger than your final velocity. But if you want to know more about that, I think it's in, yeah, I think yeah, fluid dynamics covers that a little bit more in detail. Okay, now we're getting into a very important part of the course, or well, probably where a lot of your points are going to be situated in the final, and that's going to be solving cycle problems. So you'll have 3 different types of cycles, and these equations will really help you solve most of the problems in the cycles. So you'll have the quality equations, which we saw before. So if you have you're in the mixture phase and you know your quality, then you can find whatever specific intensive property you are trying to study. Or maybe it's the other way around. You know all these properties except for quality, and you just find quality. Usually, again, so choosing between CV and CP is usually because your cycle or whatever process has constant pressure. So that would, in that case, you would choose CP. But if your process or cycle has constant volume, then you would choose CV. And usually, actually, in a lot of the exercises, if we go back to your first law equation, if your reformat maybe dE dt is equal to 0, you have no heat transfer in this case. There's no kinetic energy, no potential energy, like that. And so you can rewrite the equation like this. And let's say it's steady as well, so that the mass flow rate at the inlet is equal to the mass flow rate at the exit. And so you'd just be left with UI, so specific internal energy at the inlet minus the specific internal energy at the exit. And so so work is equal to the mass flow rate times the specific internal energy at the inlet minus specific internal energy at the exit. So here you can see, you can all agree with me, that this is the change in specific internal energy within your controlled volume. So the inlet and the exit of your controlled volume. So now if you were to go back to that equations, right here, you can see it's the same thing. It's this change in specific internal energy. And so you can equate that to CV times dt. Now, most of the case, you won't be using that long equation which you saw in the property tables. It'll most of the time be equal to this. CV will be considered a constant, or it can be either given to you, you're going to have to find it in your property tables. So it can be taken out of the integration. And so if it's just like this, if it's just, if you were to ignore the CV right here, it's just the integral from T2 to T1 with respect to dt, then it would just be this, right? This is usually the form you'll be using. It's the same for this one, but it will replace delta U by delta H and CV by CP, but it will be delta U or delta H is equal to either CV or CP times the change in temperature. That's usually the form you'll be using it, not like this integral form. And yeah, and it is very heavily used. These equations are very heavily used in the cycles, in cycle problems. The simplified form most of the time. As well, you're gonna have your polytropic equations, which we saw for how to calculate work. Again, if you were to have a polytropic or isentropic process, polytropic, isentropic, these two big words, you can pretty much use these equations. Well, only this equation if you were to have like a fluid, well, a liquid, and all 3 equations if you had an ideal gas. And if you remember, I mentioned N. I didn't really talk about it. It's a constant, and usually it's equal to 1.4. So if the exercise doesn't say what n is equal to, then equate it to 1.4. Or actually, we just saw that it was also denoted in your property tables. But usually it's equal to 1.4. And also n can be replaced by the letter k. It's just sometimes the exercises give you k minus 1 divided by k. It's the same thing. It's just n or k, same thing. They just denote it sometimes differently. And then lastly, ideal gas equations, very important. So either in this format or this format. They're very, very often used. Okay, so moving on to cycles. First off, starting off with the Rankine cycle. I mean, this is the dumbed down version of how it works. Pretty much you're inputting work into a pump so that you can have, I think, pressurized water, and it goes into a boiler with heat transfer going in, heats up the water, I think into a vapor state. It goes into the turbine, rotates the blades into the turbine, you create work, comes out of the turbine, goes into a condenser, and heat transfer goes out, and then the whole cycle restarts. You don't need to like know how this whole system works. I would just memorize like each item. So the pump, the boiler, the turbine, the condenser, and apply like a number in between each item. So here they did it. They put 1 in between pump condenser, 2 between boiler and pump, etc. And that's going to be important because you're going to have specific properties for these stages of water or whatever fluid is being used in these cycles. And so this cycle actually can be translated to a temperature. This is S. S is the letter to represent entropy. You can see the classic bell curve that we usually use. And actually, this graph could be asked of you. You could be asked to draw this graph, and yeah. So I would memorize this. It's gonna be the same as well for the other cycles, Brayton cycle and Otto cycle. They might ask you to draw these graphs. Okay, so what's important is that what's going on with water when it's going from state 1 to state 2, state 2 to state 3, state 3 to state 4, state 4 to state 1. It's very important to know that what ideal property they will have assigned to it when they're going through that process. So from 1 to 2, for example, it's isentropic, meaning that you can use the isentropic equations. They're going to be very useful if maybe you're asked for temperature at state 2, but you only know T1, P2, and P1. From 2 to 3, it's going to be constant pressure. There's going to be no pressure change, and no work is being done. From 3 to 4, it's going to be isentropic once again, and then 4 to 1, constant pressure again. And as well, from 1 to 2, you're going to have work coming into the pump, but no heat transfer. It's going to be adiabatic. From 2 to 3, there's no work being done, but there is heat transfer going into it. 3 to 4, same thing. There's work this time going out, but it's adiabatic, so no heat transfer. And the 4 to 1, there's heat transfer coming out, but no work is being done. What else? What's going to be said? So in a lot of the problems, actually, you'll be asked how much work is being created, or how much heat transfer is coming out to the condenser. You're going to be given some properties for state 1. Like maybe you're going to be given pressure for state 1, but you know that there's constant pressure from state 4 to state 1, so you know that pressure at state 1 is equal to pressure at state 4. So this example applies to other properties as well for the different states. And so it's going to be up to you to find the different properties that are going to allow you to either, maybe the question asks you to get the turbine to work, or maybe get the thermal efficiency, which we'll cover in a bit. Okay, so polytropic and isentropic, just to go back if you didn't know this. So there's a difference between the two. So polytropic means that in between two states, again, it's reversible. So if you're going from state 1 to state 2, if it's polytropic, you can go from state 2 back to state 1. Isentropics is the exact same thing, but it's also adiabatic, so there's no heat transfer. Hence why we just say an isentropic here to make it simpler. So for state 1 to state 2, not only is it reversible, but there's no heat transfer going in. Same thing for state 3 and state 4, in between, well, the process between the two. So you can say that a process that is isentropic is polytropic, but not the other way around. Okay, so there's actually a slide that I stole from Dr. Amon's slides, but it's very useful in the sense that it's giving you the accessional equations that you'll need to solve a lot of the ideal Rankine cycle equation problems. So you'll have equations for the pump, the boiler, the turbine, the condenser. There's the equation for the pump and the turbine. You'll have the work equations. For the boiler and the condenser, you'll have the heat transfer equations. And you may be asking, like, where did these equations come from? It's the first law equation, very simplified. dE dt is equal to 0. For the pump and the turbine, it's adiabatic, we saw, so heat transfer is equal to 0. Assume all the time that its kinetic energy and potential energy are always equal to 0. So you're just left with work, mass flow rate, and specific internal energy. Or this version, using this version of the first law equation, not specific internal energy, but specific enthalpy instead. And so for the condenser and the boiler instead, for example, where again, dE dt will be equal to 0, kinetic energy and potential energy will be equal to 0, but this time work also will be equal to 0, and Q won't be equal to 0. And so that's how you've obtained these equations. So either you can just memorize the first law equation and then again apply it for each process, but that takes a while. I would just memorize these instead. And yeah, it can either be the specific enthalpy change or the specific internal energy change. You will get the same value. Usually for Rankine cycles, they pretty much all the time use specific enthalpy. Same thing for Brayton cycles. But for Otto cycles, they pretty much all the time use specific internal energy. Okay. You could be asked as well. Yeah, these slides will be posted on Moodle, don't worry. Along with all the other the slides for all the previous tutorials that I did. So yeah. For the work net, so that's just the total work of your entire system. Is going to be the work of the turbine plus the work of the pump. All the time, your work from the turbine should be positive. If it's negative, and what's probably happened is that you took the wrong, the difference between the specific enthalpy, you put it in the wrong order. So you put H4 here and H3 here. And so you got like a negative value. If that happened, then that means you need to reverse the order, because the work in turbines, coming out of the turbine is always positive. That's imperative that you memorize that. And for the pump, it's just the other way around. It's always negative, because you're putting work into a system. You're losing work. So pretty much usually, like for example, maybe the work of the turbine will be 500 kilojoules and the work of the pump will be minus 200 kilojoules. So your work net will be 300 kilojoules. A very simple example. I don't know if I cover it. Do I cover it? Okay, I do a little bit. I'll cover it now. You may notice that in a lot of your exercises, heat transfer work are denoted in different letters. Well, different letters, in different forms of the letters. you'll have the lowercase, you'll have the uppercase, and then you'll have the uppercase with the dots on top. The lowercase, so for work and heat transfer, pretty much means that they are in the intensive format. So they'll have, usually they'll be represented in the kilojoules divided by kilograms units format, and they'll be denoted once again in the lowercase form. So work, heat transfer. Well, specific work and specific heat transfer. In the uppercase form, it's not independent from mass. It'll just be in the kilojoules format. In the uppercase with a dot on top, that means now they are independent from time. So pretty much what that means is that you'll have kilojoules divided by seconds. And actually, one important thing is that in these cases, they'll here they'll say specific work or specific heat transfer. Here they're going to say work and heat transfer. Here, most of the time, they'll just say heat transfer once again. And for this one, they can either say work with respect to time or independent of time, or power. This is just power. This force over distance, this is force times distance divided by time. It's just equal to power. So it's very important that you make this distinction, because sometimes you'll just see the W in different, or the Q in different shapes and form. That's pretty much what they mean. And sometimes in exercises, they may ask of you, hey, we want the work, but then in the exercise properties that they give you, mass is not included. So then you can only use this format because it's independent of mass. If mass is included, then you can use this format. Okay. Another important thing is how to go from one another. So how to go from here to here or here to here. So to go actually from W dot to lowercase w, it's going to be W dot divided by mass flow rate. It's going to give you like that. So that's going to go from power to specific work. Now, if you just want to go from power to work, then it's very simple. W dot times time, or whatever, like the range of time you're studying your process for, it's going to give you work. And it makes sense, right? Because you're multiplying kilojoules by seconds, so these cancel out, and you get work. And if you want to go the other way, actually, wait, from specific work to work, then it's just lowercase w times mass is equal to W. Makes sense again, because kilojoules divided by kilograms times kilograms cancel out the kilograms, and you get the kilojoules that you want. And if you want to go the other way around for all these, then you just reverse the equation. So for example, if you want to go from specific work to power, then just multiply specific work by mass flow rate. Same thing for the other equations. Okay. Okay. Yeah, okay. Thermal efficiency. So this says thermal efficiency for Rankine cycle, but actually it can be applied for any cycle and any process, really. It's just going to be your work net divided by the heat transfer going in. Actually, you can see here that it's in lowercase w, so it's specific work divided by specific heat transfer. That's just a side note. So thermal efficiency is work net divided by Qn, and that can also be equal to 1 minus specific heat transfer going out divided by specific heat transfer going in. And that's because work net can also be written as specific heat transfer going in plus specific heat transfer going out, just like it's going to be equal to, well, we saw that right before, the work of the turbine plus the work of the pump is the same thing, work going out plus work going in. Okay. One also very important thing, thermal efficiency can only go from 0 to 1, or well, 0 to 100%. If your thermal efficiency is higher than 100% or 1, then you messed up somewhere. That's Actually, one observation that we notice about that, take the absolute value of this. It's really hard to write with the mouse, but take the absolute value of this this fraction, and you should get something smaller than 1. It's very important that thermal efficiency be smaller than 1, because then you show the teacher that you understood the concept. Yeah, so again, this note states that work pump in is always going to be negative. All right, in Brayton cycle, it's pretty much the same principle as the Rankine cycle. You have different items within your cycle that have in between them different states of whatever fluid you're using. So your compressor, heat exchanger, turbine, heat exchanger. Actually, just replace this heat exchanger by the word boiler and this heat exchanger by the word compressor and condenser, sorry. And you have the Rankine cycle. There's not really that much different, actually, is there? Constant pressure, isentropic. Yeah, they're pretty much the same. I think the only difference is maybe the fluid that you're using in it. Is usually in Brayton cycles you're using gases, whereas in Rankine cycles you're using liquids. But same thing. So from 1 to 2, so from the inlet of the compressor to the outlet of the compressor, you have an isentropic. So again, that's adiabatic and a reversible process. From 2 to 3, it's constant pressure with heat going in. So you have heat transfer going in, isentropic. 3 to 4 pretty much is the same thing as 1 to 2. And 4 to 1 is pretty much the same thing as 2 to 3, but other way around. And again, so from 1 to 2, you have work going into the compressor, so you're losing work. That should be, again, negative. And from 3 to 4, you're creating work with the turbine, so you have positive work being created. And with these two, no heat transfer is being made. On the other side, with the two heat exchangers, you either have heat transfer going in or heat transfer going out, but no work is being created. Okay, and then you have the equations. The heat transfer or the work equations, depending on what you want to study. And again, you can either memorize these or understand the first law equation and how to reformat it to gain these values. And they also directly here, they give us the change in specific enthalpy is equal to Cp, if Cp is just a constant between these two states, times the change in temperature. And, well, you can equate that to work in and work out as well. Cp, like here, would be Cp T2 minus T1. Okay. And you can use thermal efficiency as well in here. It doesn't change. Oh yeah, and this side note covers, again, how to transition from the power to the work to the specific work, or other ways around. I'm not too sure. So yeah, kilojoules, kilograms to watts. So that's specific work to power multiplied by mass flow rate. Yeah, exactly. Oh yeah. I saw this in one of the exercises. They may give you instead of like the pressure from state 1 and state 2, they could just give you the pressure ratio. Say maybe pressure ratio is equal to 8. So you know, from state 1 to state 2, you have a pressure change. From state 2 to 3 or state 4 to 1, you have no pressure change. But state 1 to 2 or state 3 to 4, you have a pressure change. So if you have, for example, a pressure ratio of 8, and that just means pressure at state 2 divided by pressure at state 1 is equal to 8. Or the other way around, the pressure at state 3 is equal to divided by pressure of state 4 is equal to 8. Usually it's P2 and P3. If you select 2 to be right here in between the compressor and the heat exchanger, and state 3 to be between the heat exchanger and the turbine, then this applies. If it's smaller or equal, well, it can't be equal, but if it's smaller than 1, then it's the other way around. It's it'll be P1 divided by P2 or P4 divided by P3. You just memorize that P2 and P3 are larger usually than P1 and P4. Also, they can ask you sometimes, I see that quite a few times, what is the highest temperature? What is the highest pressure in the whole system? So usually the highest temperature will be in state 3. So in between the heat exchanger and the turbine, or in the Rankine cycle, it's in between the boiler and the turbine. Or what is the highest pressure? Then I just told you it's either in between the compressor and the heat exchanger or heat exchanger and turbine. Okay, finally, the last cycle. So that's the Otto cycle, or pretty much any piston cylinder device. You can casually see them in your car. So like a gas-operated car. So instead of having a turbine, etc., you have a piston cylinder device. There's a lot more cool videos that can describe these processes in more detail. And I think in Thermo 2, you also see cover them in a lot more detail. But for here, it's very simplified. So from state 1 to state 2, what's happening is that your piston is going up into your cylinder. And that creates, from state 1 to state 2, an isentropic compression. So you're gaining pressure in an adiabatic process. And to move the cylinder up there, then you're going to have to put work in. So you're losing work. So this is going to be the state where your work is going to be negative. Then from 2 to 3, you usually have like an explosion going in. So happening right here, due to since it's compressed, pressure is added, and I think like another fluid is added or something, and then an explosion occurs, and that creates heat transfer. Heat transfer is going in. So from state 2 to state 3, the explosion happens, and you have constant volume heat addition. Then due to this explosion, from state 3 to state 4, your cylinder comes back down. So just like with state 1 to state 2, you have an isentropic expansion, not compression, but expansion. And then state 4 to state 1, you have no work is being done, but you have heat coming out of the system. Okay, and you have your respective PV diagrams. So just to recap, from 1 to 2, you'll be having work going in, losing work. State 3 to state 4, work is being created from the piston going down. So you'll have positive work, and then the heat transfers from state 2 to state 3 and state 4 to state 1. Some of the vocabulary that can be used in the Otto cycle is the bottom dead center and top dead center, which pretty much means bottom dead center is the maximum volume that you can get. And that pretty much means that your piston is at as far down as it can go. And then top dead center is the other way around, it's the smallest volume. Your piston is as far up as it can go. The bore is the diameter of the piston, though I've never really seen that in exercises. They don't actually, no, they could say the bore of the piston is I don't know, 4 millimeters, and then you would have to calculate the surface area of the piston, just like I said before, the surface area of the piston, and calculate the force of the pressure of the air onto the piston surface. But I haven't seen the word bore in many of the exercises. And then stroke is just the length, so how far your piston can travel. Okay, Otto cycle not only has thermal efficiency right here at the bottom, but it also has mean effective pressure. So an exercise can ask you, hey, what's the mean effective pressure of Otto cycles? And that's just the work net divided by the difference in volume. So the difference in volumes between your strokes. So when the piston is all the way at the top and when your piston is all the way at the bottom. And you can see it's in different formats. So you have your work here divided by the change in volume, whereas here it's specific work divided by the change in specific volume. So just make sure that they're in the same units, or I guess same format, not same units, but same format. Then moving on, you have the compression ratio, which we talked about right before. It's going to be this time. No, we talked about pressure ratio. This is the compression ratio. So instead of pressure, you're going to have the volume. So the volume occupied by the air at the bottom dead center. So that's the maximum volume that you can have, and then volume occupied by the air at the top dead center. So the minimum volume that you can have, which logically will have always a value bigger than 1. Now, like I mentioned before, in Otto cycles compared to Brayton cycles and Rankine cycles, you won't be using specific enthalpy to calculate your Q in, your Q out, your work in, your work out. You'll be using specific internal energy. So I don't have it here, like I don't have this slide, but for the Otto cycle, but pretty much it's going to look very similar to that, but instead of it being U3 minus U2, H3 minus H2, it'll be specific internal energy at state 3 minus specific internal energy at state 2, or is equal to not CP, but CV times change in temperature, right? If you remember from right here again. So change in specific enthalpy is you use CP, space change in specific internal energy, you use CV. Okay. All right, I think this is the last part. Yep. So chapter 6, or the second part of chapter 6, the first part was the cycles. Just thermal efficiency. We go over it a little bit more in detail. You have different forms of how you rate thermal efficiency right here. Just a note also for like the upcoming stuff, sometimes they use different lettering for Q. Instead of Q in or Q out, they use QH or QL, but it's pretty much the same thing. So QL is just Q out and QH is Q in. So heat transfer low is equal to heat transfer out. And same thing for high is equal to in. Okay, so now we're going to study 3 different types of, I would call them processes, but I would call them systems instead. So you have heat engines, refrigeration cycles, and heat pumps. And I guess the idea behind the second law of thermo is what you can't do. So the first law of thermodynamics doesn't put into detail what can't happen in the universe, like you have to respect the laws of physics. Second law of thermodynamics explains these limitations and how to apply them when you want to study something in the real world. So, for example, the first Kelvin-Planck statement is it's impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. So pretty much what it's saying is that this guy is impossible. You can't just have heat going into what seems to be like a turbine system, heat going into a turbine system and just having work created. You have to have heat transfer going out. You have to have a QL or a Q out. Okay. And the other statement, which could be asked of you, I've seen some like questions in past finals where they ask of you some definitions. It is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a lower temperature body to a higher temperature body. So let's say, for example, you're in a classroom and you bring a cup of tea that's at room temperature. It's at the same temperature as the classroom. It's impossible to make it warm, make it at a nice temperature that you'd like to have your tea at without implementing work. That's pretty much what this statement is saying. You can't just go from a lower temperature to a higher temperature without implementing work. Okay, so just to go back to like the different systems that can be asked of you, you have heat engines. usually, so the furnace goes into, for example, like a volcano's magma chamber is going into a turbine system, and work is being created, but you also have to reject some heat, and its efficiency can be calculated this way. For refrigeration cycles, well, you all have fridges at your home, I hope, and there's not just thermal efficiency that you can calculate. Actually, you probably won't be calculating thermal efficiency for refrigeration cycles. You'll be calculating something, the coefficient of performance, and so that's going to be your QL, or again your Q out divided by your work net. Or if you were to rewrite this, so rewrite work net is equal to QH minus QL, can be rewritten in this format. Okay, and I would memorize these equations again. Either ask your professor to give you the equation sheet that they're going to give you for your final, to get a better picture of what equations are going to be given to you or not, so that you know which ones you need to memorize. Okay, and then heat pumps. You'll notice that actually heat pumps and refrigeration cycles, with the diagram on the left, have the exact same form. So you have a cold refrigeration space that's inputting heat transfer into a system. Work is being implemented into that system, and then heat transfer is coming out. Okay, so just like with the fridge, sometimes there's maybe especially with like old ones, you can feel the heat coming out of some certain sections. So the cold section, which is inside your fridge, inputting heat transfer into your system at the back of your fridge, and work is coming in from your power grid thanks to Hydro Québec, and then heat transfer is coming out. So especially, like I said, with old fridges, you'll feel like warmth coming out of certain sections of your fridge. And with heat pumps, it's the other way around. So like you're in a cold environment and you want, your room temperature to be higher. So you raise your thermostat, and again, Hydro Québec comes in to save the day, and you get warmth input into your room. Even though the diagrams are the exact same, your coefficient of performance equation will be different. So instead of QL, it'll be QH divided by work net. And again, you can reformat the equations from the work net equation in here. And well, this isn't really needed, but coefficient of performance of a heat pump is equal to the coefficient of performance of a refrigerator plus 1. One thing very important to note, again, thermal efficiencies are always equal or lower to 1. Whereas coefficient of performance are either equal to 1 or above. It's very important to know. Okay. All right, this should be the 3 last slides. So Carnot cycle efficiency. So in some exercises, they may ask of you, what is the highest efficiency or coefficient of performance that can be obtained with this system? And Carnot, some guy in the past, created this equation, which is pretty much you replace your thermal efficiency equations or your coefficient of performance equations. You replace the heat transfer with your temperature. So let's take the heat engine. So your furnace is at a temperature of 100 Celsius. And your river is at a temperature of 0 Celsius. So 373 divided by, well, no, here it would be, so QL would be replaced by your temperature low, and your QH would be your replaced with your temperature high. So here 273 up top, and at the bottom 373, and then 1 minus that. So let's say maybe 0.25. 1 minus 0.25 is equal to 0.75 or 75%. And for your system, that would be the maximum efficiency that it can get. It'll never get there, obviously, but that's the maximum. That's like its peak that it can attain. So actually, if you calculate something that's above the Carnot efficiency, or in the case of the coefficient of performance, lower than the ideal or Carnot version of this coefficient of performance, then that means you messed up. It can't be, or the purpose of the exercise is to show that whatever system is being analyzed is impossible, then it's wrong, pretty much. So it can't be higher than the thermal efficiency, or it can't be lower than your coefficient of performance, the Carnot version of it. Okay, entropy. So this is the last part. So what is entropy? It's just for theory's sake, it's a thermodynamic quantity representing the unavailability of a system's thermal energy for conversion into mechanical work, often interpreted as the degree of disorder, randomness, blah, 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 whatever. A good example of this is it's just stuff that universe throws at you that makes your system even less ideal than you anticipated it to be. So for example, in a piston cylinder device, when the cylinder goes up or goes back down into the cylinder, it hits the walls slightly, or it's like friction being created in between the piston and cylinder, reducing the efficiency of your cycle. So entropy is something that you just cannot get away from. Now, obviously, since this is university and a lot of the exercises are very ideal, sometimes entropy is equal to 0, meaning that you have no loss, no efficiency loss. And when your entropy is equal to 0, that means your processor is reversible. Again, so when your processor is reversible, your mind should immediately go back to polytropic and the polytropic equations. If S is not equal to 0, then your process is irreversible, meaning you can't use the polytropic equations. Entropy, entropy is an extensive property. So here you see it's denoted by uppercase S, but it can be denoted as intensive property, as it is in your property tables. It just divided by mass, and you can go from an extensive property to an intensive property. Two different ways to calculate entropy. So either directly with the property table. So you're given two independent intensive properties that will give you a specific entropy through the property tables. Or you can use, especially when you're dealing with ideal gases, you can use these two equations. So the change in entropy is equal to this or this, depending on whether you have access to CV or CP, or if you have, instead of having the difference in specific volume, you have the difference in specific pressure.